So we are going to continue our interpretation of quantum mechanics, the interpretive part. So in this class, so we are going to have corpuscular interpretation and relate it with our previous thing, how we try to see how probabilities could be taken account of before and after measurement. So how we can sometimes omit certain probabilities in a chain, and whether we cannot omit. If we can omit, it gives a certain tautological or a logical interpretation, and otherwise also we can interpret things in the other way. So in today's class, we are going to have some idea of this corpuscular interpretation, which we have seen in previously also. For example, any variable, a quantity, a measured value q, a measured value q, we can have a simultaneous value p, and vice versa. So you can, the way we have conjugate parameters p and q, e and t. So you can see for any measured value, you can have a conjugate parameter. So the question is, once we take unobserved, what I should say, entities into consideration, so how can we interpret things? What is the admissibility, or what are the admissible? What is the admissible interpretation in presence of interpretation? So we'll see, for example, if we have a definition, admissible interpretation in the sense we can define two conjugate variables, but we have not observed one of them, but that unobserved entity is somewhat in a conjugate manner related with some another variable which we are going to measure. So how can we account for that unmeasured entity, or even though it is related to something which is we measured or we have to measure in that sense. To address it, so we'll have a definition. If a value v u of an entity u has been observed in a measurement of u, this value ui means value of u we are going to measure immediately or after the measurement. So we assign, if we have observed u, value of u has been observed, and we are assigning a measurement where u can be value immediately or after the measurement. So this is one thing. So only an intervention from outside. The intervention, so if we assume that there is non-commutativity, so we can say that that measurement is destroyed, our measurement in the absolute sense, in the classical sense, or in the sense that we can have a given measurement to a given value. So if there is non-commutativity attached with two conjugate parameters, so somehow measurement gets disturbed or destroyed. So probability relation can be probability of S is the state, it's the initial measurement of this. You can also have it probability, you can define it. S is the state, M is the measurement of this state, U, so you can have its value. You can also write it, so you can say that U exists before measurement also. This means that what we are going to measure, its value is the same value which we have measured before the measurement. So before the measurement or after the measurement, the value should remain same in that sense. So now we have to account for that if it's related in some conjugate manner, this thing that our measurement before and after should remain same, somehow it will not be that valid in that sense. So we're coming to that argument. So if a measurement Q has been made, we can express this convention of, so we now can have two measurements, probability of mu, so it's before and after, you can say it's probability of measurement ui, and this is mv vk. So the formally we can express, if we have this is one equation, this is second equation. So we can express our convention with vis-a-vis. So this is the thing rule. So now we have to see. So if we have in a single measurement, so it's besides the point to mention that probability or our measurement after this measurement was the same value what was before the measurement. Now, if there are two conjugate entities such that in the quantum mechanics, one is related to the other, you cannot have simultaneous measurements because of non-commutativity. So if we cannot have simultaneous measurements because of non-commutativity, so the thing is that for example, so if we have two values, for example, before and after, so ui and vk can existing at the same time. So namely, simultaneous means two observables can be simultaneously measured, mu and mv can be simultaneously measured. So knowledge of this can be, so ui measurement of initial variable, it will be u. So initially its value before measurement was ui. Even after measurement it would be ui. And the other parameter is vk and vk. So it's before measurement and after measurement. Before measurement, but they are not simultaneously, they are not conjugate variables. So if they are conjugate variables, so you cannot, so this statement, this thing is not to be, so we have to see how we can at least state this point in terms of this thing. So if we want to write it, if we want to state it, that probabilities before and after measurement may not come out to be same. So you can say that this principle that before and after measurement for individual variables can come out to be same for two variables. But if there are conjugate variables, the simultaneous measurement, so this principle, we say that this uh, principle does not apply for a combination of simultaneous values. So you cannot use this knowledge of simultaneous values. So you cannot, if it's not true for two presents, two simultaneous values. So our extrapolation towards the prediction of future becomes suspect. Even you cannot even say it has come from a common past. These two simultaneous conjugate variables, their measurements, if they don't, they don't remain same before and after measurement. This means you cannot trace them to some common past from a given past, or you can have not have a you cannot have an extrapolation or prediction in that sense. That's it. So we can say knowledge of simultaneous values for predictions of results of future measurements. So this is this. So the future is undetermined. Future is undetermined. Why? Because the knowledge acquired is no longer valid for the affairs. So knowledge you have acquired, it's no longer valid the moment it was acquired. Acquired knowledge at the moment or at the measurement we are saying. So it's intrinsic in the postulates, in the way we define things. And so we cannot have inference for the into past either. Yes, yes. Now the same thing what we have said it. So we can have this was one thing. You can have these. So if I write it here, so we'll write it here. This equation 1 and 2, probability of S of ui is probability of S1. So before measurement and after measurement, it will remain same. MUI, UI, MV, VK. So if this thing, this is equation 1 and 2, now we can have another we can have another definition. Here the previous one was definition 1, so definition 2. So now we are going to connect the same thing. This is the normal statement that simultaneous measurement of two observables at a given time at the same time cannot be lead to the same measured values. Individually, the measurement can be same, but it's the point of simultaneous measurements of two conjugate variables. Now the question is that leads to both problems of predictions for the future or any inference in relation to past. Now the point is that we have to do the same thing for probability analysis, and what we did in our previous class. How we could connect two probabilities, and we could sometimes in the intermediate chain, if there are two events and we can have measurements. So we are interested in the first initial and the final state, what we get as an outcome after repeated measurements. If the repeated measurements are held for a given amount of time, or if the notion of time is not involved in that thing. So our prediction is independent of the intermediate values. So we can take the first value and the last value, provided the times as is not explicitly involved in our measurements. So that's what we had seen in the previous class. But now, using the same understanding, so we can say the probability of combination Vk relative to physical situation S or physical state S is given by product of individual probabilities. So we can have product of this state Vk omega m. So we can write it. So sometimes if we remember the probability may be sum of the probability square. So sometimes it leads to contradictions, or it will not lead to contradictions if in the previous class if we assumed that this inequality doesn't hold. If I remember, so previous to the previous class, the interpretation was, yes, this thing. If this mu, ui, mv, mw is not equivalent to, if this interpretation was not, if you say it is not equivalent to this, means we can, intermediate states can be ignored. So if it's not, then that's fine. If we take yes. So you can say this probability of state this and this can be probability of state Vk into probability of state this, or probability of state if you combine it with relation 1 S Vk, we can have probability of S Mv Vk, probability of state S M WWM. So you can have two observables. The probability of two observables can be taken as probability of two individual observables separately. Or, so here the state can be psi also, a quantum mechanical state psi also, which on which the measurement is being done with a measurement used. So probability of this mu, ui, vk, you can also write it for two measurements. You can write it as ui, vk into probability of mu, ui, wm. So you can write it. This is for one measurement. This is for two measurements. You can write it for this way. Or here u1 we can have this here. You can have probability of mu, ui, mv, vk, of probability of mu, ui, mw, wm. So definition 2 states the independence of Vk and this omega m. So Vk and omega m are independent from this definition. This means probabilities do not depend upon in the conjugate sense. So you can independently measure. Total probability of these two measurements is independent of these individual measurements. So we can also use absolute value of probability, and this means we can replace equation 4 and 6. 4, if we have, this is 4, this is 5, this is 6, this is 7. So we can replace 4 and 6, means this and this equation can be replaced by the formula probability of S of Vk omega m can be written as probability of S of omega m. So you can ignore this one of the parameters here, or probability of S mu ui Vk omega m. So you can see we can sometimes from this thing we can ignore this S of u can be written as this. So we can write it. So we have used this equation, these two equations here, and written this thing. Sorry, we have used. So we can replace 4 and 6 by the. We can replace this and this by this by this, and this by this. Means we have taken from S and omega. So V has been ignored, and here also K has been ignored. Yes. So that again you can remember in a given chain. If there are repeated measurements, one interpretation of probability is that if the time involved is not too much, or we can ignore time, so we can the intermediate events they can be ignored. We can take the initial and the final states regarding the measurements. This is one thing. Or if we use now this and this in this equation, so it will turn out that m of ui, first we'll write a probability of, probability of, so now if you assume it this way, now applying this and this on this, so you can turn out probability of S of Vk omega m is equal to probability of S of Vk omega m is probability of S m omega m, or probability of S mu ui Vk omega mu ui Vk is equal to probability of so we can say it like this. So the same should hold for we can also consider the expressions this thing. The relations 8 and 9. So if it's these are 8 and 9, this is 11 and 12. So we have done nothing. We have seen idea of how measurement of observables simultaneous two or more measurements of two variables. So how we can write them in terms of probabilities, and using a particular interpretation of probability, such that probability of a given event is probability of those individual measurements, whether this thing is possible or not. So if we have a probability of two measurements, is as if you are measuring one is probability of for example u probability of v, and then probability of uv taken together. So question is probability of uv taken together, whether it's equivalent to probability of u into probability of v separately. So this is the question. So if we assume it that way, a simultaneous measurement of two probabilities of two variables, whether that's equivalent to the measurement taken individually. So if that idea is true, and we just rewrite these parameters this way, so we can have these relations. Yes. Now, if you remember, in first case, if it's true, so there were two interpretations. The frequentistic interpretation. If it's not true, then we have to ignore this identity. Means that if for times are not that much, or if time is not a factor, so our measurements in one logical interpretations or tautological interpretations, so these statements can be equal. The initial measurement we have to be only take consideration in a repeated set of measurements. The initial state and the final state becomes important, and the intermediate states can be ignored. In the other case, we cannot ignore it that way. So if it's that frequentistic interpretation, then if we can ignore it in the tautological sense, probability of this and this should be equivalent to probability of S V1. These are different events. These are the intermediate events. And this is so we can write it as these intermediate things can be ignored. So normally we are involved in two conjugate variables. So we can say it probability of S Vk is equal to probability of S Vk, or at the end you can see probability of S Wm into probability of S Vk is equal to probability of S of W. So it's a small proof that so here we have assumed that probability of S of Vk, its total probability is 1. So you can say, so we can ignore these intermediate things. We can see this thing. So this shows that we can show that the rule 9, this rule 9. So our rule 9 does not contradict our rule of the relative probabilities in the earlier sense. So now we make one couple of statements. Vis-a-vis these two rules which we have seen, that measurement of one parameter or measurement of two conjugate parameters, these two statements, we can have an exhaustive interpretation. One was, if you remember in the start of the course, we started with restrictive interpretations and the exhaustive interpretations. So if we can have, since in this class we are more interested in the unmeasured entity. So we can have measurement of two variables, so their measurements before and after will come out to be same, one or more. But if there are two conjugate measurements, and one of them is unknown, undetermined, so but we have taken measurement of one variable, so it is going to affect the simultaneous measurement of the other variable. Now the question is, or the unobserved entity. So we can have, we can, if I write this statement, which somehow summarizes things. We can have general theory of meaning, meaning in the sense, in the philosophical sense. what we actually mean by what we are doing in that sense, that that interpretive statements about simultaneous values of non-commutative entities have truth meaning for situations between two measurements, and probability meaning for general statements. So this means for interpretive statements about simultaneous value of non-commutative entities have truth meaning for situation between measurements. So for the simultaneous non-commutative two conjugate variables, so our measurements cannot be absolute in that sense. Yes, that's it. And and generally also otherwise, if they are not two conjugate simultaneous, the measurements are not simultaneous for two conjugate variables, they are generally means that measurement before and after for a given variable or more than one variable, they will more or less they will come out to be same. After some repeated measurements, you can arrive at the same value. So the probability statements can also hold generally also. So we have to make distinction that for simultaneous measurements, the probability statements may not hold in that sense. Yes. Yeah. So this was the summary of this class. So we are going to continue this next. Thanks.